Welcome to the heart of electronics. Every gadget you use, from your smartphone to your laptop, relies on a fundamental component, the resistor. Today, you will learn to identify the 10 most common types of resistors, understand how they are constructed, and recognize their specific roles in electronic circuits. By the end of this video, you will be able to choose the right resistor for any application, whether you are looking for precision, power handling, or environmental sensing. Let's dive into the building blocks of modern technology. We began our journey with one of the oldest and most established types, the carbon composition resistor. These are made by mixing finely ground carbon with a binding material, usually a ceramic or resin, and then pressing it into a cylindrical shape. The main advantage of these resistors is their ability to withstand high-energy pulses. Because the entire body of the resistor is a conductor, they don't fail as easily under massive surges compared to film-type resistors. However, they are becoming less common today. This is because they have a high tolerance, meaning their actual resistance might be quite different from what's printed on them, and they tend to be noisy and less stable over time, as they absorb moisture from the air. Think of these as the old reliable for heavy-duty surge protection, but not for precision timing or sensitive audio equipment. Next, we move to a more modern standard, the carbon film resistor. Unlike the solid composition type, these are made by depositing a thin film of carbon onto a ceramic rod. The resistance is precisely controlled by cutting a spiral groove into that carbon film, almost like a screw thread, to increase the path the electricity has to travel. Because the carbon layer is so thin and the manufacturing process is more controlled, these are significantly more accurate and stable than carbon composition resistors. They also generate less electrical hiss or noise. Take a look at the color of the body. While carbon composition is often tan, many modern carbon film resistors use a light blue or beige coating. They are the workhorses of general electronics, found in everything from toys to simple household appliances. When your project requires high precision and low noise, you reach for the metal film resistor. These are constructed similarly to carbon film resistors, but instead of carbon they use a thin layer of metal, typically nickel chromium, deposited onto a ceramic base. Why does this matter? Metals are much more stable than carbon when the temperature changes. If your circuit gets hot, a carbon resistor's value might drift, but a metal film resistor stays remarkably consistent. They are the gold standard for high-fidelity audio equipment, medical devices, and instrumentation where a tiny error in resistance could lead to a big problem. If you see a resistor with 5 color bands instead of 4, there is a very good chance it is a high-precision metal film type. Remember, when accuracy is your top priority, metal film is the way to go. When a circuit needs to handle a massive amount of power without melting, we turn to the wire wound resistor. Unlike the film resistors we've seen, these are made by literally winding a metal wire, usually an alloy like manganese or nichrome, around an insulating ceramic or fiberglass core. Because the wire can be quite thick, these resistors can handle very high currents and dissipate a lot of heat. This makes them perfect for power supplies, industrial heaters, or motor controllers. One interesting detail, because they are essentially a coil of wire, they can act like an inductor at high frequencies. This means they are great for DC power applications. But you wouldn't want to use a standard wire-wound resistor in a high-frequency radio circuit unless it was specifically designed to be non-inductive. In summary, if you see a large resistor that looks like a miniature radiator, it is likely a wire-wound resistor built for heavy lifting. Understanding resistors, the building blocks of electronics. So far, we have looked at resistors with a fixed value, but what if you need to change the resistance while the circuit is running? That is where the variable resistor, commonly known as a potentiometer, comes in. Think of the volume knob on an old radio or a light dimmer switch. Inside, there is a resistive track and a sliding contact, called a wiper. By turning the knob, you change the position of the wiper, which varies the amount of resistive material the current must pass through. Most potentiometers have 3 pins. If you connect to the 2 outer pins, you get the full fixed resistance. But if you connect to the center pin and 1 outer pin, you create a variable path. This mechanical adjustability makes the potentiometer the primary bridge between human input and electronic control. It allows us to physically dial in the exact behavior we want from our devices. If a potentiometer is meant for the user to turn, the trimmer resistor is meant for the engineer. Trimmers, often called trim pots, are tiny variable resistors mounted directly onto the circuit board. You won't find these on the outside of a device. Instead, They are hidden inside, used to fine-tune a circuit during the manufacturing process. For example, a trimmer might be used to calibrate the exact zero point of a digital scale or to set the precise frequency of an internal clock. Unlike the sturdy knob of a potentiometer, trimmers are designed to be adjusted once or twice with a small screwdriver and then left alone for the rest of the device's life. They are the set-it-and-forget-it version of adjustable resistance. When you see a tiny screw on a circuit board, you are looking at the final touch of precision engineering. What if we want the environment to control the resistance? Meet the thermistor, a resistor that is highly sensitive to temperature. There are two main types of thermistors you need to know. The most common is the NTC, or negative temperature coefficient thermistor. For these, as the temperature goes up, the resistance goes down. They are perfect for temperature sensors in digital thermometers or car engines. The second type is the PTC, or positive temperature coefficient thermistor. These work the opposite way. When they get hot, their resistance increases sharply. Because of this, PTC thermistors are often used as self-resetting fuses. If a circuit draws too much current, the thermistor heats up, its resistance skyrockets, and it chokes off the current to protect the components. Whether it is sensing the heat of a laptop processor or protecting a lithium battery, thermistors are the thermal guardians of electronics. Imagine a streetlight that turns on automatically at dusk. This is often made possible by the light-dependent resistor, or LDR. The LDR, also known as a photoresistor, is made of a light-sensitive semiconductor material like cadmium sulfide. When light photons hit the wavy track on the surface, they knock electrons loose, making it easier for electricity to flow. In total darkness, an LDR might have a resistance of several million ohms, but under bright sunlight, that resistance can drop to just a few hundred ohms. Specifically, remember this rule. Higher light intensity leads to lower resistance. This simple but effective property makes them ideal for light meters in cameras, night lights, and solar tracking systems. They allow a circuit to see the world around it by translating brightness into a measurable electrical signal. In some circuits, a component needs to be both a worker and a bodyguard. This is the role of the fusible resistor. A fusible resistor is a specialized component designed to protect a circuit. Under normal conditions, it behaves exactly like a standard resistor, limiting current to a specific value. However, if there is a fault and the current exceeds a safe limit, the resistive element inside is designed to melt or open in a controlled way. Unlike a standard resistor, which might catch fire or smoke when overloaded, a fusible resistor is built from non-flammable materials to ensure it fails safely, breaking the connection like a fuse. You will often find these in power adapters and television circuits, acting as the final line of defense to protect more expensive components and the user from electrical hazards. Finally, we look at the tiny giant of the modern world, the SMD chip resistor. If you open up a modern smartphone or a high-end graphics card, you won't see many of the large, through-hole resistors we've discussed. Instead, you will see thousands of these tiny rectangular specks. SMD stands for Surface Mount Device. These resistors don't have wire leads. Instead, they are soldered directly onto the surface of the board. This allows for incredibly dense and compact circuit designs. The numbers on the back, like 103, tell us the value. Just like the color bands, the first two digits are the value, and the third is the number of zeros. So, a 103 is a 10,000 ohm resistor. Because they are so small and have no leads, they are perfect for high-speed automated assembly by robotic arms. They are the reason our devices can be so powerful, yet fit in the palm of our hand. We have journeyed from the heavy-duty carbon composition and wire-wound resistors to the microscopic SMD chips that power our digital lives. You should now be able to identify these 10 essential types, from the precision of metal film to the environmental sensing of thermistors and LDRs, and the safety of fusible resistors. Each one plays a unique role in controlling the flow of electricity, ensuring our circuits are accurate, powerful, and safe. By understanding these building blocks, you are now equipped to design, repair, and innovate in the world of electronics. Thank you for exploring the invisible forces that shape our modern world. Keep building and keep learning.